Hello everyone, Chickenfuck here. Today I'm going to be proving this algebraic property regarding syndromes in quantum error correction. This is basically saying that the syndrome of a product of two Pauli operators is the modulo 2 sum of their individual syndromes. And this makes the syndrome map a homomorphism. Before proving that, I figured this looks really confusing, but don't worry, we're going to go through everything, so let's jump right into it. Rather than asking what is this state, it asks, does this state still satisfy some algebraic checks? And those checks are called stabilizers. So when an error occurs, it can change how the error operator commutes or anti-commutes with these stabilizers, and then we encode those relationships into a binary object called a syndrome. Now that we have this base, let's jump into the math. So first things first, let's go over the errors, okay? So for a single qubit gate, we have Pauli errors, I, the identity, which does nothing, X, which does a bit flip, Z, which does a phase flip, Y, which combines bit flip and phase flip behavior. So for multiple qubits, we might write X tensor product, I tensor Z, right? The set of n qubit Pauli operators, including the relevant phases, forms the Pauli group. So whenever you see P, N, right? What this is saying is Pauli operators acting on n qubits, okay? That is what this notation means, which is over there. So now let's go over quantum error correcting code. So basically, instead of storing one logical qubit on one physical qubit, what quantum error correction does is store information and distributes it across multiple physical qubits. So this is how this might look. So we can write our logical basis states as so, for example, 0L, 1L. We can also write an arbitrary qubit as such. So these encoded states form a subspace, which is called a code space. So now let's define with notation a quantum error correcting code. Okay. This n is the number of physical quantum systems. The n is the number of logical quantum systems encoded. And then the Q is the dimension of each physical system. So for ordinary qubits, this Q will be 2. In other notation, especially for binary stabilizer code, you will often see this way of writing it, right? Where D is the code distance. So we won't need the distance for this proof, but it tells us how small a non-trivial logical Pauli error can be, and therefore how many physical errors the code can detect and correct. Now, let's get into stabilizers. Let's suppose Pauli operator G satisfies this equation for every state in the code space. Then G is a stabilizer, and then the full stabilizer group is written as S. S equals So what this is saying is this angle bracket means the group generated by these operators, right? So this means the group generated by these operators. So G1 through Gn minus k are independent stabilizer generators. So then when we say S is less than Pauli n, that means that S is a subgroup of the n qubit Pauli group. And then these generators are the checks we're going to compare possible errors against. Why is this n minus k? Because for a binary stabilizer code, the n physical qubits give a Hilbert space dimension of 2 to the n, and then each stabilizer condition selects a +1 eigenspace and has the dimension. So then after n minus k independent constraints, we have 2 to the n over 2 to the n minus k equals 2 to the k. And 2 to the k is the exact dimension needed for logical qubits. Before we go in further, we need to go over something else. Poly operators either commute or anti-commute. Commuting means this. And anti-commuting means this. So for example, this is commuting and this is anti-commuting. Spoiler alert, this minus sign is going to become a syndrome bit. So now we're going to go into the syndrome map. Define the syndrome map as such. And this maps G, where G is in Pn. So what this is saying is that G is in Pn and the output is a binary vector. So the output is, okay, this is what this is saying here. Basically, we have poly operator to binary syndrome. Now we might ask, what is this? What is that about? Let's explain that. So the individual syndrome bits are defined as such. L, J of G equals 0 if G, J, G, 1 if G, J, G. So what this is saying is that if they commute, you get 0. If they anti-commute, you get 1. What this is saying is that we compare the error G against every stabilizer generator, G, J, record either 0 or 1, and then collect those bits into the syndrome. But then why does this detect an error? Suppose that psi L is a valid code state. So that means that it satisfies G. L equals to, suppose that error G and the state becomes G psi L. If G commutes with G, J, so in other words, if G, J, G equals G, G, J, then it's a bit long, but if what happens if G commutes with G, J, we see this as being true. So the stabilizer eigenvalue is still +1. If G were to anti-commute, what would happen? Okay, if the anti-commute, you get this, right? As you can see, the eigenvalue becomes -1. So that's why the syndrome bit is encoding something physically meaningful. The +1 implies 0, and the -1 implies 1. So now let's decode this F2 here, right? So the F2 is the field containing just 2 elements, 0 and 1. But the arithmetic is modulo 2. So that means that 0 plus 0 equals 0. 0 plus 1 equals 1. And 1 plus 0 equals 1. And then 1 plus 1 equals 0 mod 2. Last one is especially important. By the way, if you don't know what mod is, it's just a remainder after division. So then what is F2 to the n minus k? F2 to the n minus k is just the set of binary vectors with n minus k entries. So for example, if n minus k is 3, then 0, 1, 0 is in F2, 3. And that's exactly what the syndrome looks like. So I put down an example to make sure that we're all on the same page, right? So what we're saying is, let's say an error E occurs, right? So we have 3 stabilizer generators here, G1, G2, and G3, and that error occurs. We compare E to each generator. As you see, For the first one, they commute, so therefore L of E is 0. So if you remember, the L is basically like a yes or no test, right? So as you can see, we have 0, which means they commute. For the second one, we have a 1, since there's a negative 1 here, meaning they anti-commute. And then for the third one, we have 0 because they commute. So then we just add those individual answers and we get 0, 1, 0, which is our syndrome. The vector is our syndrome. That's all it's doing. Let's jump into the problem now. I basically wrote this down here. So let's unpack this first. What does the symbol here mean? This means modulo 2, component by component. So for example, if I had 1, 0, 1, mod 2 of 0, 1, 1, I would get 1, 1, 0, because we're taking mod component by component. Okay, now what is a homomorphism? It's a map that preserves the algebraic operation. So here the domain is Pn, where the relevant operation is multiplication. The output is F2, it's F2 n minus k, where the operation is binary vector addition. So to show the syndrome map is a homomorphism, we need to show this statement, which is exactly what this question is asking us to prove. And this home HOM Pn F2 n to n to the k just means the set of homomorphisms from Pn to F2 n minus k. So here is the proof. Let H1, H2 be in Pn. And then we're going to let Gj, this is going to be one of the n minus k stabilizers of S. N minus k stabilizer of n minus k generator. So we have Gj, which is n minus k generator of the stabilizer S. So the first thing we want to write down is -1 to the L J H1 H2 GJ H1 H2. Now, why do we write this down? Is that the LJ tells us whether H1 H2 commutes or anti-commutes with this GJ. So therefore, using this equation, we write down GJ. So this is just a compact commutation relation from the definition. Now we want to move JG back toward the left, okay? So we first use the definition on H2. So we have 1 H2. GJ equals H1 of -1 LJ of H2, then GJ H2, okay? So why? Because I said, again, LJ tells us whether H2 commutes, this with a Z, tells us whether H2 commutes or anti-commutes with GJ. If it commutes, the factor is +1. If it anti-commutes, the factor is -1. So now we use the same relation for H1, okay? Okay, so please bear with the notation, but I wrote it out the last step here. So altogether, we have this equation. What this is saying is that the operator part is the same on both sides. Therefore, the signs have to agree. So blowing this up a bit, H1, H2 equals -1 to the LJ of H1 plus LJ of H2. Because each LJ is a binary, we only care about parity. Therefore, LJ of H1, H2 equals 2. So this has to be true, right? And then we can rewrite this using that notation and write LJ of H1, H2 equals LJ of H1. So use the mod 2 operator, here, and agree. So we can say this is true. Now we need to extend this to the syndrome. So basically right now I'm just writing down the syndrome of the product. And then using the result we just proved for every component, we would get L1, H1, modulo 2, L1, H2, L, n minus k, 2. We get this, right? So by the definition of binary vector addition, we must get sin q of H1, H2 equal to sin from q, H1, modulo 2, sin q of H1. So we would get this statement, exact statement we're trying to prove here. Why do the two anti-commutations cancel? Suppose AH1 commutes with GJ, that's 1 minus sign. Suppose H2 also commutes with GJ, and then the -1 times -1 equals what? It equals +1. So the product can commute even though each individual operator anti-commutes, and the modulo 2 captures that perfectly. The 1 mod 2 1 equals 0, which is why the binary arithmetic works naturally in the stabilizer error syndromes. So why does this prove homomorphism? We know that syndrome H1 H2 equals this, right? So multiplication in the poly group is being translated into addition in a binary vector space. So the syndrome map preserves the group operation. Therefore, this statement is true. That's the mathematical meaning of the final line in this exercise, right? Now let's go into the kernel. Once we know the syndrome map is a homomorphism, another important structure will emerge, which is the kernel. So the kernel is the set of poly operators that map to the zero syndromes. The zero syndrome means that every component is 0. So then L of H, so Lj of H would equal 0 for all J, right? And then 0 means commute. Therefore, these operators would commute with every stabilizer generator. Zero syndrome does not mean no error, though. That's very important. So the identity has 0 syndrome, but every stabilizer also has 0 syndrome. Certain logical poly operators can also commute with every stabilizer while still changing the logical information. The 0 syndrome basically means invisible to the stabilizer checks. So whether that's harmless to the operator, it depends, right? So the kernel connects to the normalizer because in the poly setting, these are the operators that commute with the stabilizer group. And the stabilizer itself lies in the set. But operators in N of S as non-trivial logical operators. So then the question you might ask is, why does this matter? Why do we go through all this work? Why does any of this matter? Because syndrome extraction is one of the core mechanisms in quantum error correction. The physical noise acts on encoded qubits. So we perform stabilizer measurements. And then those measurements produce a syndrome. A classical decoder analyzes the syndrome and decides on an appropriate recovery or a polyframe update. Go from noise to stabilizer measurements to syndrome to decoder to recovery, right? So why is the homomorphism result important? Well, this is saying that when the poly errors combine, their syndrome information combines linearly over F2. So what that means is that we can manipulate syndrome information using binary linear algebra instead of tracking huge quantum states or giant matrices. So surface codes routinely measure stabilizer checks, and that allows us to infer error chains, right? That's it, I guess. Thank you so much for watching.